Hello everyone, and welcome to this next video lecture. So today I want to talk more about linear regression. As you can guess, it's a pretty big topic in this class, being able to do the least squared regressions line, and to think about these ideas of best fit line for a scatter plot. So recall when we were calculating correlation, it didn't matter in what order we chose our x and our y. So in the case of how we've been calculating correlation, one, I guess we can calculate it by hand. And two, we've been using this Corel function. And you remember you put the x values and then the y values, close parentheses, press enter, and it'll give you the correlation between those two numeric variables. Recall also that I showed us that if we had put the two values in the opposite order, so y values and x values, we would have gotten the same thing. And this actually makes sense when we look at our formula. What was it? R equals n minus 1 sum of xi minus x bar over sx times yi minus y bar over sy. And they're specifically the same thing regardless of if you do x and y or y then x, because these two values, the product of two numbers, is commutative. Which means if I flipped these two, it would give us the same answer. And that's why it doesn't matter if you do x and y or y then x, because the calculation is the same regardless. So my question for us is this also true for our least squared regression line? Well, let's try to build some intuition into this. The least square regression line is this y equals b0 plus b1x, right? And I gave you the formula to find each of these. So b1, I believe, was r times sy over sx. And b0 was y bar minus b1x bar. So if we were to flip the x's and the y's here and instead do a sort of, I guess, x equals b0 plus b1y, note that these two values would actually change. If we were to calculate the same thing for this sort of flipped equation, we would have, I'm going to distinguish these with stars. We would have b1 star is equal to r times s of x over s of y. So already it looks like our slope is different. And since the slope is different, I believe the intercept is also going to be different. So at a glance, it appears that maybe these lines are not the same. But let's try to motivate that a little bit more with some pictures. So our x-axis here is the distance of a galaxy from Earth, and y is the velocity at which the galaxy is moving away. And note the two lines here. The solid red line is the line that we would get if we were predicting the y-axis with the x-axis. So the red line, and I'll write it in red, is this one right here. Okay? The dotted red line is the line that we would do it if we had flipped the axes and done the same thing. If we tried to use y to predict x. So this one is the dotted line. So indeed, it would appear that they are not the same. And we can see that sort of by looking at the differences between these formulae right here. Or we can actually see that by thinking about what the least squared regression line is doing. So recall that least squared regression minimizes the sum of the squared, and I'm going to say vertical, residuals. So in the case of our solid red line here, and I'm going to zoom in, the solid red line is the one that minimizes the squared distances between these points and the line. Right? We would take all of the distances between these points in the line, square each of those distances, sum them up, and that should be the minimum possible distance of any other line. Is the dotted line doing the same thing? Is it also looking at the vertical distances? And the answer is no. And I have a picture to sort of illustrate this as well. If we do it the other way, if we use y to try to predict x, you should think of it as if we had done the same problem except we had flipped the axes. And when we do that, this new line of ours is not actually minimizing the sum of vertical square distances, it's doing the sum of the horizontal square differences, because it would actually be vertical if we were to flip these two axes. It's basically doing the original calculation except with the axes flipped. So therefore, if we look at them on the same axes, the dotted line actually minimizes the sum of squared horizontal distances, which is a very different line. And that's why we get two different lines when we flip them. So regression is not like correlation. If you do one on the other, that is not the same thing as doing the other on the one. Okay? So this is one point, something we should know about regression, is that order does indeed matter. Next thing I want to talk about is other criteria for minimization. So we decided to think about the sum of squared residuals. Why didn't we think about just the sum of the residuals? That is, if I had something like this, recall I have a line and I look at all of these vertical differences between the line and the points. And I find the line that's, if I were to square all of these values, the line that would make that sum of squares as small as possible. But why didn't I just add up these values, right? Why didn't I find the line that made just the distances, the vertical values as small as possible? And the answer is, think about these two cases. So what if I had just 2 points like so? Well, the least squared regression line is very clear in this case. The one that minimizes the amount of sum of squared vertical distance would actually just be this red line right here, right? So our best line in this case is just the line that goes to the 2 points, and that's because the sum of squared residuals in this case is 0. There are no residuals because we were able to fit the 2 points exactly. Now say if I were to think about the sum of just the residuals. In this case, for this first one, the sum of residuals is equal to 0. We don't see any residuals whatsoever. What if, instead of that line through the 2 points, I drew this line? So I would not say that this is the best line, right? It doesn't fit the data nearly as well as this first line does. But make a notice. What are the vertical residuals here? They are 1 and -1. Therefore, the sum of the residuals is equal to 1 plus -1, which is equal to 0. So if we had used just the sum of the residuals, both of these lines, oh goodness, I wrote that a little bit wrong, didn't I? Give me a moment. This is -1, my bad. So if we just use the sum of the residuals, we get these two lines that are both best by our criteria, and it's clear that one of them really isn't as good as the other one. So we do indeed need to square residuals because we run into this problem of residuals sort of canceling each other out. There is another criteria that does work though, if we wanted to use it. And that is if you thought about this, the magnitude of the residuals. So you could build a regression line that minimizes the magnitudes of the residuals. So we wouldn't have this problem with residuals canceling each other out in this case. What we would do is we would have all of these vertical lines, right? We'd have all of our residuals. And I would call this one like R1. This is like residual 2. This is residual 3, residual 4, et cetera, et cetera. And I would find the line that makes the sum from I equals 1 to n of the absolute value of the residuals as small as possible, which is just 1. And the picture of this actually looks like this. Oh, oop, wrong one, sorry. This one. So this is a scatter plot, and the solid line here is our usual least squared regression line. And the dotted line is the line that minimizes the magnitudes of the residuals. Okay, and look, these lines both actually fit the data pretty well. They're slightly different, certainly, but with different criteria, we get different lines. In this class, we're mostly just going to do least squared regression, so we're only going to be thinking about the squares of the residuals. I did want to let you know, though, that this choice of thinking about the squared residuals isn't the only choice, and you can actually do it different ways. One of the reasons that people stick with least squared regression is because you get this nice formula, right? We had, towards the beginning of class, we had this, we have this specific formula for the slope and intercept of the least squared regression line, whereas if you had minimized the magnitudes like I'm presenting to you here, you wouldn't have that same nice formula. You would have to do sort of like an optimization problem that is, you know, that would actually be difficult for me. That's not an easy problem to do. So the final thing I want to do today is I want to show you how to draw a least squared regression line in Excel. So I hope you can all see my Excel sheet. And here's the scatter plot that we've been looking at quite a number of times. And if you want to add a least squared regression line to a scatter plot, what you do is you go to chart design, you go to add chart element, and you choose a trend line and linear forecast. And boom, there is a least squared regression line right there. If you right click it and press format trend line, you can actually have it display the equation and the r squared value on the chart. So let me do that right now. And look at that. This is actually our least squared regression line right here with the slope and the intercept. Excel has calculated it for us. And the r squared value, the coefficient of determination, which I think by now we've spoken about. Also, just a little side note is I usually find this little blue dotted line not that clear, so often I like to make it a little thicker and make it a color that really jumps out, which I did red in this case. So there we go. This is now a scatter plot with a least squared regression line fit to it. and an r squared posted for us. So that's how you do it in Excel. And that is all I wanted to talk about today. So thanks, everyone.